aggregates, daily aggregates, and so on. And one very interesting thing that I found really useful when analyzing and working with blockchain data is that you have so many different types of data types, and you can get a lot of value from combining these data sets. So for example, in this chart, this is actually from a blog post I wrote a while ago about analyzing the Bitcoin blockchain with Postgres. And here we analyzed the transaction volume, which is the green line, versus the BTC USD rate, which is the yellow line, and analyze how they correlate. And why I think this kind of analysis is really, really interesting, because these are two different data sets. So on one side, you have the transaction volume, which you might be able to get from directly the blockchain by ingesting on-chain data, and then you aggregate all the transactions into, I think in this case, probably daily or weekly aggregates. And then you combine this data set with another data set which has cryptocurrency data, which has the BTC USD rate. And again, this is all happening within the database. At least that's how it should be done, because otherwise, there are some time series databases where you cannot store different types of data sets within the database. And so what ends up happening is that your time series data will be in one database, in the time series database, and then your other relational data will be in another database, and then you need to sort of combine them on the application layer, and that can be a headache. With TimescaleDB, you can store any kind of data within TimescaleDB because we are Postgres. So you can store anything in TimescaleDB because we are a general database, but we are also do a lot of optimizations for time series, aka blockchain data. And this is another raw data example that can be used as a data set in your data application database. This is from the Bitcoin blockchain. So this is on-chain data and a few of the columns. Again, you can notice that we have a time column here, which is really important because that's one of the columns that you use to join this data set with other data sets. We have block ID, hash, size, weight, and we can have other columns like whether it was a Coinbase transaction, block size, etc. And if we look at this raw data, and we look at the previous raw data example from a different data set, we can notice a few things. And these are all, both can be considered blockchain data because they show you information about the blockchain, but both data sets are time-stamped. So they are time series data, again, because blockchains are technically time series databases. They are append only. You only add new records to the blockchain or blocks to the blockchain. You never go back and modify historical blocks unless you are Ethereum, because in that case, that might happen because it happened once. But fortunately, we don't do such crazy things in Bitcoin. Anyway, also blockchain data is real-time data, which means that new data is being processed on the blockchain as we speak. And so if you're building a data application and you want to be real-time, then you will need to find a solution so your database can actually deliver performant real-time data, which is not necessarily easy with analytical databases, and that's one of the key reasons users try TimescaleDB, because even though TimescaleDB is a relational database and we are good for analyzing historical and analytical aspects of the data, we also have the specific features that are not available in other relational databases to give you real-time performant data at the same time in the same database. And finally, blockchain data is connected to other data sets. What I mean by that is that blockchain data can be joined with other data sets, like, for example, in the chart where I combined the transaction data set, the on-chain data set, with a cryptocurrency data set. And you can do this with mining metrics. You can pull in, even if you are a business, you can pull in internal data and combine that with the blockchain public data. So there are a lot of possibilities to explore, and that's one of the reasons I'm really interested in blockchain data, because all the data is out there. Everything is public. You just need to take the time to analyze the data and see how data can help you do whatever you're trying to do. All right, now with that said, what kind of database is best for storing blockchain data? Based on the previous examples, because blockchain data is time series data, you need a database that is scalable for time series data. Within TimescaleDB, the foundation for time series scalability is that we use auto partitioning based on the time column. So whenever even though we are Postgres, whenever you insert data into a table, under the hood, it will get partitioned into multiple tables based on the time column. And that sort of provides the foundation for long-term scalability for your time series data. Next, historical and real-time capabilities. Again, this is, I think, really useful because real-time workloads are very different from historical, or real-time queries very different from historical or analytical queries. And also, if you want to provide real-time data that's on a customer-facing application, for example, that can be really hard to do in the same database with your historical workloads as well. And with TimescaleDB, we also have a solution for this because basically we have a way to combine the historical pre-aggregated data with the real-time data that is aggregated on the fly. And that is something which is not available in Postgres and not available in any other relational database. And then finally, avoiding data silos. Again, this is super important if you're trying to combine multiple data sets. And after a while, if you get started with exploring the Bitcoin blockchain, or if you get started exploring cryptocurrency data, you will probably want to combine some other data set, and it's good to be prepared for that. And fun fact: the founders of Timescale actually created TimescaleDB because they were building a data application, and they found it really hard to combine time series data with other data sets, and they spent a lot of time doing implementing this on the application layer, and they spent whole developer sprints coding something that really should be done within the database. And talking about Timescale, this is where TimescaleDB really shines. As I mentioned, we are open source. We are free. You can find us on GitHub. You can try it for free. And we also have a cloud offering if you want to go in the cloud. And here's just a quick overview of the TimescaleDB architecture. As I said, we are based on Postgres, which means that we are not trying to be Postgres-like or similar to Postgres. We are Postgres because we are an extension, not even a fork. So basically, on the bottom, you see the storage layer. The storage layer is the same that you can find in Postgres. And if we go upwards, we modify the schema management and the query planner. So the schema management layer We introduce auto-partitioning. That is what I mentioned. We partition your data based on the time column. And that provides long-term scalability. Also, because of the auto-partitioning, you get a lot of nice features. Like, for example, if you want to drop data, like let's say 1 year, 2 years, because you won't need it anymore, in a regular relational database, you would just do like a delete statement, which would delete all the rows one by one. With our auto-partitioning, or what we call chunking mechanism, you can set a data retention policy to get rid of all data that is older than, for example, 1 year, and it's not going to do delete statements, which can be slow. It's going to do it's just going to drop tables. So it will drop whole chunks, and then it's going to be much faster, much more efficient because of the chunking mechanism. And then we sometimes modify the query planner, especially if you run time series queries when you're filtering by time or when you're aggregating by time, which is something you would very often do if you are analyzing blockchain data. Maybe you're creating 1-day time buckets, or you're creating 5-minute time buckets. And we have features that make it easier for you to do that and make it more performant. And then finally, the SQL layer, the SQL API. We are full SQL, meaning everything that works in a Postgres database will work in a TimescaleDB as well. So it doesn't take anything away from Postgres. We just add a lot of new functionality, like, for example, time series functions that help you analyze time series data and blockchain data. For example, we have functions that help you create the values needed to create candlestick charts. So you can generate the open, the high, low, and close values within the database from raw data. And then we also provide a bunch of other statistical functions that can be useful to analyze blockchain data. Now, I won't have time to go super deep on all the TimescaleDB superpowers and features. I would just like to highlight, maybe 2 of these, and then go deeper in one of these. So first of all, these are the high-level features that TimescaleDB adds on top of Postgres. So first of all, we have compression, which can help users save on disk storage needs. A lot of our users get 90 to 95% or even more compression rate, which is really great because they can save a lot of costs. And while they save on storage needs, the data is still, you can still query the data, and some of the analytical functions, some of the long-range queries where you are querying a long range of data, those are actually faster if you turn on compression, which is really interesting, really, really useful because you get multiple really impactful benefits. The other flagship feature that TimescaleDB has is continuous aggregates, which is what we are going to break down in the next few minutes. They are basically materialized views for time series data. Who here is familiar with materialized views? Great. So, so you probably know that in Postgres, dealing with materialized views can be a little bit hard, mainly because if you want to refresh them, if you want to keep them up to date, you always need to refresh the whole thing. Like, you cannot refresh just the most recent time period, like, for example, the last 15 minutes or 1 day, which is really inefficient for blockchain data, because as we mentioned before, blockchain data is time series data, and you always just add new things to the blockchain. And if you refresh a materialized view, the whole thing will need to get replaced, even though obviously nothing changed in the past on the blockchain. Unless you are Ethereum, of course, but let's not talk about that. Then we have data retention, which is, again, a feature which I believe is really specific to time series data, because what we found is that users often find time series data less valuable as time goes on. So older data becomes less valuable. Sometimes they just compress it because they want to keep it. But sometimes, other times they just delete it and they set up a data retention policy so it gets removed after 6 months, 1 year, 2 years, 5 years, etc. User-defined actions, multi-node cluster, and hyperfunctions. If you're interested in these, you can look them up in the TimescaleDB documentation. But I would like to go a little bit deeper in continuous aggregates, because when we talk about Bitcoin data applications, I think continuous aggregates are really the feature that you will need. And current customers like Messari, we also have FTX, the exchanges customers, they all use continuous aggregates because this is just such a useful feature to build data applications. And why is that? And the reason is that continuous aggregates basically provide a foundation for data applications. They provide a foundation for performant and maintainable blockchain data apps. And let's see how it works. So as I mentioned before, continuous aggregates are very similar to materialized views. The difference is that it supports real-time data. So unless with regular materialized views, where you need to refresh all the time the view to keep the data up to date, with continuous aggregates, you can get access to real-time data, even if you don't refresh it all the time. And basically what happens is that, as you can see on this image, you have raw data, which can be blockchain transactions or raw cryptocurrency tick data, and then you aggregate the data into 1-minute time buckets, 5-minute time buckets, daily time buckets, whatever time range you are trying to analyze. And then as you have new blocks added to the blockchain, you always update the materialized view. But even if you don't update it, maybe you have 90% of the data updated in the materialized view, so that portion will come from the materialized table. The other 10% is not materialized yet, and that's another problem for TimescaleDB. It can generate the aggregates on the fly when you make the query, and that's actually really useful for real-time data applications because 90% of the data is coming from a pre-aggregated materialized table, and only 10% will need to be aggregated, and that's why it can stay fast. The query can execute really fast. And because of this, as I mentioned, the refresh mechanism of continuous aggregates are much more efficient. In this example, all the gray dots represent data that is already materialized. It's already pre-aggregated, meaning if you create a dashboard or visualize data, then the user can change filters and interact with the dashboard, and it will be fast because everything is coming from disk. Except the last maybe 10% or less, which is not yet pre-aggregated. It might take 10 minutes, an hour, 2 hours, depending on your policy, until that portion will get aggregated as well. And so when you make the query to the continuous aggregate, that little portion will be calculated on the fly, but that's so little data that it doesn't impact performance that much. And this is how you would create a continuous aggregate. As you can see, if you're familiar with materialized views, it's very similar. You need to use the create materialized view command with TimescaleDB continuous, and then you can just define the definition of the view. In this example, this actually shows a candlestick aggregate. So you have the symbol, which can be, for example, BTC USD trading pair. Then we have a hyperfunction called a time bucket. This is not available on Postgres. This is a function that aggregates data based on time. And this example creates hourly time buckets. And then the next in the next line, we use the first function, which is also a hyperfunction, which creates selects basically the first price value ordered by time, which is going to represent the opening price of that specific candle. And then we have max, min for the highest and lowest price, and then finally the last, which is the opposite of the first hyperfunction, which selects the last price value ordered by time. And this is a very typical setup. Many people create continuous aggregates similar to this if they are dealing with candlestick aggregates. All right, so finally, I don't know if we're going to do Q&A. I would be really happy to do Q&A. But just a few things to remember. So as I said, blockchain data is time series data. And that's true technically, like the data points have timestamps attached to them, but also time plays a huge role how blockchains operate and how people analyze them. So if you build a data applications, you will also need to focus on time, because people will probably look at different time ranges. They will look at the trends. They're interested in the time aspect of blockchain analysis. In order to build blockchain data applications, you need a database that has exceptional time series capabilities. Again, this is important because even though Bitcoin is a relatively simple blockchain compared to some others, but still you have a lot of data, especially if you are ingesting raw transactions and you are ingesting miner info, you are ingesting crypto prices, so this can be a lot of data, and you need a database that is able to scale out based on the time metric of the data set. And if you decide to try TimescaleDB, use continuous aggregates. Again, this is one of our flagship features. They are fairly easy to understand and implement, and yet they provide really, really great benefits if you're especially if you're building customer-facing analytics, or maybe even if you're building some software that is not a traditional data application, but you have some portion within the software which provides analytics for the users. We have a lot of those use cases. And I highly suggest checking out our crypto resources page, timescale.com/crypto. We have a lot of tutorials, hands-on tutorials that teach you how to analyze Bitcoin data, blockchain data with TimescaleDB. We also show you how to get access to data. So if you don't have a data provider already, we show you an example how to write the data pipeline, how to ingest it into TimescaleDB, and we show you simple queries that you can maybe later use to build a blockchain explorer, build a cryptocurrency analysis tool, or if you are building an app, a customer-facing analytics feature. All right, so that was me. I'm available on Twitter and email. I'm happy to chat with everybody online, but also after this talk and tomorrow. And yeah, a bunch of other resources. Thank you very much. So this is the last talk. I don't know if we can do Q&A. I would be happy to do Q&A if people have questions. Yes, we can do. Anybody has questions? Yes? Yeah, so the question is about SQL versus NoSQL databases, and whether there are like bottlenecks when it comes to blockchain data. Yeah, so one of the things that, so I see a lot of people migrating away from NoSQL databases to SQL databases, mainly because with SQL, by using a SQL database, you get a lot of benefits. Like, for example, you can use all the tools that connect with SQL, like all the visualization tools, and you also get the benefit of having a relational database. So you can use one relational database to store both the time series, your time series data sets, alongside with your other relational data sets. And so you can do very simple joins within the database. With a NoSQL database, sometimes it's hard to, for example, generate those candlestick aggregates in a NoSQL database. I don't want to say the name of the company, but I was trying. It's one of the time series databases, a NoSQL time series database, and it's literally 40 or 50 lines of code to do the same thing that we did in like 10 lines of code in TimescaleDB, and they're just crazy. And yeah, as I said, the founders of TimescaleDB created TimescaleDB because they got tired of trying to join data on the application layer. So yes. Any other questions?
Hi. What's about how to load the data? Is there a way to handle the blockchains as streaming tables and so on? Or you load the tables, the data to the tables, the crypto tick with CSV and so on, like classical way, or you know what I mean?
Yeah, how to load data into TimescaleDB. So because we are Postgres, you can use any Postgres connector library in any language, and you will be able to load data into Postgres. We have tutorials that show you how to implement these. We have tutorials that show you how to bulk load data from CSV file, how to connect to APIs, how to connect to WebSockets. But yeah, basically you can just use the standard Postgres tools, and that will work with TimescaleDB as well. Does that answer your question?
No, I mean more rich features like connecting directly to the blockchain itself, like a streaming table, Spark things.
So I know a few companies in the crypto space who are working on that, and we are actually starting to partner with one of these startups, and they will enable direct connection between your Postgres database and on-chain data. So I think that's what you're looking for, and I think that's, companies are working on it. Yeah, but currently you need to implement your own solution. Any more questions? If no, then thank you very much.